Well, good afternoon, everyone. Thank you so much for coming over to Mitchell Hall this afternoon. We are gathered to hear Levi Thompson give his inaugural lecture. My name's Robin Morgan. It's my great privilege to be the provost, and Levi was, I suppose, the first dean whose employment letter I signed, so that's pretty fun. Levi became the dean of the College of Engineering this past fall, and today he's going to deliver his inaugural lecture as the Elizabeth Inez Kelley Professor of Chemical Engineering. I think many people know he is a Blue Hen. He's a UD alum. He graduated with a degree in chemical engineering here in 1981. He then went to Michigan, where he earned a master's degree as well as a doctoral degree in chemical engineering. At Michigan, he came up through the ranks and was named the Richard Ballheiser Collegiate Professor of Chemical Engineering. He also served as Associate Dean for Undergraduate Education from 2001 to 2005, Director of the Hydrogen Energy Technology Laboratory, and also Director of the Michigan Lewis-Stokes Alliance for Minority Participation. His research area is nanostructured materials for catalytic and energy storage applications. He is co-inventor, he holds more than 10 patents, and co-founder of 2 companies. So I remember when Levi interviewed, he talked about the difference between innovators and entrepreneurs. And he specifically mentioned, I wrote it down and I pulled my sticky off your application today. Some people are good at turning money into concepts. That's most faculty. But turning concepts into money is much more difficult. Do you remember saying that? Okay. Levi is also a fellow of the AICHE and the recipient of many awards, including the 2006 Michiganian of the Year Award, the National Science Foundation Presidential Young Investigator Award, the McBride Distinguished Lectureship, Union Carbide Innovation Recognition Award, and Dow Chemical Good Teaching Award. So lots of plaques on the wall. Levi was also very active in the community in Ann Arbor, serving on the Board of Trustees for the Ann Arbor Area Community Foundation and the African American Endowment Fund. In short, or in long, a very distinguished career. We're proud to have you on our faculty. What's been Levi's key to success? Your colleagues reached out to a few of your folks you know for some insights. So hang on, Levi, you might want to sit down. Again and again, we heard descriptions of Levi as a brilliant researcher, teacher, mentor, and entrepreneur, whose energy, passion, and drive to succeed set him apart as an outstanding leader and expert in his field. We also heard a lot about his great sense of humor, which we have also appreciated. Johannes Schwank, the James and Judith Street Professor of Chemical Engineering at the University of Michigan, advised Levi for his PhD. Johannes recalls his earliest memory of Levi in his lab. Are you ready? The hills are alive. Yeah. He was singing the sound of music at the top of his lungs. Scott Fogler, the Venema Professor of Chemical Engineering and the Thurnau, I hope I'm pronouncing these reasonably well, Professor at the University of Michigan. For him, it wasn't music or movies, but rather a love of basketball that helped to establish the early connection with Levi. After finishing his graduate studies, Levi accepted a job at Ann Arbor, and Scott, who then chaired the chemical engineering department, recruited Levi for a faculty position. I knew he would be an excellent teacher, and at the end of the first semester, the student evaluations confirmed that. Over the next few years, Levi continued to distinguish himself not only as a teacher, but as a researcher and an entrepreneur. David Martin, the Carl and Renate Bohr Chaired Professor of Materials Science and Engineering and the Associate Dean for Research and Entrepreneurship. David, I don't know if you're here. I can't see because of the lights, but thank you for your comment. First met Levi when they were both junior faculty members at the University of Michigan. He said something, he mentioned something that always impressed him, and that was the way Levi, and his wife Maria worked together as a team. They created a company, TJ Technologies, in 1991, very early in Levi's career, and in 2006, they sold the company at just the right time when it was near the top of its market value. Dave described Levi as a role model in many ways, including his forays into academic leadership and his focus on the design and characterization of materials that are technologically and commercially relevant. Susan Montgomery, G. Brymer Williams Collegiate Lecturer at Michigan, first met Levi when they were students and later worked alongside him as a faculty member. As a fellow minority faculty member, it was my pleasure to work with Levi to improve the environment for minority students. I appreciated his willingness to host minority students in his research lab, to participate in panels and other events, to encourage minority students to strive for success, and in so many ways to advocate for change that in the end helped all of our students. And so it is now my great honor to introduce the Elizabeth Inez Kelley Professor of Chemical Engineering and Dean of the University of Delaware. I was supposed to advance that, Levi. Dean of the University of Delaware College of Engineering. Levi, the hills are alive.
Thank you.
Thank you so much for giving us the pleasure of this presentation.
Well, thank you, Robin. So I want to thank you all for being here, my friends, my family. Robin mentioned my wife who flew in from Michigan to be here with us today. What an honor it is to be here, not only because I graduated from the University of Delaware, but also because of all the wonderful things that I've seen since I got back. And I'm truly honored to have been selected to be the Kelley Professor. I'm also honored to have been selected to be the Dean of the College of Engineering. We have a wonderful faculty staff and student body that I am every day grateful to work with, and so I'm looking forward to the next 4 or 5 years doing some really wonderful things here. I also understand that this is being videoed or maybe even live broadcasted, so I'll say hello to my mother, who's not here, but if she's watching, hi, Mom. Okay, so got that out of the way. And obviously we're here because of Elizabeth Inez Kelley. To be honest, I didn't know very much about her before word came that I might receive her professorship in her name. So I did a little bit of research, and with the help of our communications team, learned a lot more about her. I can tell you she was a wonderful woman. I am thankful for all the contributions that she made to the University of Delaware, to the community. She was also a tremendous advocate for women and working women in particular. She also had a passion for education that is important to those of us who are here as well as those outside these doors. So as I think about what she did with her career, she, as you can see, attended the University of Delaware. It's interesting, at that time, she was enrolled at the Delaware Women's College. At that time, women and men did not go to school together, at least here at Delaware. And so later on, I think in 1945, the Women's College and the Men's College, or the University of Delaware, merged, and so we have what we now see as the University of Delaware. But she was certainly at the forefront of trying to address issues regarding education and women in the workforce. She graduated from Drexel. I grew up in Philadelphia, so in fact my brother went to Drexel, so I know Drexel fairly well. Graduated in 1919. Tremendous advocate for women in the workplace and in society, being a member of the American Women's Association, which during World War II, she was very instrumental in maintaining the Civilian Defense Information Center in Pershing Square. So, another factoid, she was the longtime secretary to the president of Merck. All of these are very important, but she also made an important statement with her contribution, which we ultimately used to retain some of our very best faculty That includes Stan Sandler. I'm not sure he's here, but Stan was one of my professors as an undergraduate. Is that Stan? Yeah. Okay, uh-oh. Now, wonderful that you're here. I can remember actually many good times and some more stressful times in his class, but always committed to excellence, which is something that I've tried to do with my career. That excellence is reflected in all the awards that he's gotten. In particular, he was recognized as a member or elected to the National Academy of Engineering. Dion, who's a colleague of mine now, one of the real inspirations behind converting biomass and other kinds of resources into fuels and chemicals, has benefited from Elizabeth Kelley's contributions to the University of Delaware. And then Eric Kaler, who many of you know as the former dean of the College of Engineering, so he stood probably in a similar place that I'm standing right now. Eric went on to become the president of University of Minnesota. He's still the president, I believe, until July 1st. Done some wonderful things. He is also a member of the National Academy of Engineering. I mentioned Mitchell Hall or standing in this place. I can remember as an undergraduate student standing out on the steps, and I have pictures of this. You know, the friends that I had at the time, we were standing there just kind of pondering what might happen. I couldn't have imagined being here in any of my visions. Most of them included basketball. Obviously, I would have loved for that to happen, but maybe my second would have been to be here and enjoy a career at the University of Delaware. You know, again, as I was thinking about Ms. Kelley, I thought about what she might ask me to describe or say as part of this presentation. And given her commitment to women and the fact that March is Women's History Month. I don't know if you knew that or not, but she would have made sure that I understood how important it is to recognize women in engineering. And so I'm not going to tell you of all the many accomplishments that women have made to engineering, but I just thought I'd highlight a few. One is a colleague of mine while I was at the university. Actually, I'm retired from the University of Michigan, so technically I'm still on their faculty as an emeritus faculty member. But Lynn Conway was a good friend of mine. She's a computer scientist. She's an electrical engineer. She's an innovator. She also is a member of the National Academy of Engineering. And while she was working at IBM in the 60s, she was part of a team that put together a computer system that today is part of the modern personal computer, the algorithms and the hardware that's in the processors for today's computers. So just a tremendous contribution. And I often ask, what would the world look like without somebody like Lynn Conway? You could ask, what would the world look like without Grace Hopper, excuse me. So Grace Hopper was Rear Admiral in the United States Navy. She led the development of a programming language for the very first computers that ever were. And so again, what would this world look like without Grace? Stephanie Kwolek, who worked at DuPont for many years. She was an innovator in the polymer engineering and science field. She developed or discovered a liquid crystal that ultimately was used in a material called Kevlar. Kevlar is used in bulletproof vests. It's used in radial tires, just a tremendous number of applications. And again, what will we do without Stephanie? How many of you recognize Hedy Lamarr? Okay, so a few of you do. She is one of the great actresses of all time. I mean, maybe not of our generation necessarily, but she's certainly one of those stars that a lot of people have heard the name before. So I didn't know this. Hedy Lamarr was also an innovator. She is responsible for the development, at that time they called it a remote control system. But really what it was a wireless communication system that allowed for, during World War II, US military to communicate between each other. And a lot of it was analog as opposed to digital, but it did allow for communication. That is the basis, as I understand it, for Wi-Fi and Bluetooth, the technology that we use today. all the time. In fact, we're probably using it right now. So this just goes to show not only that women have made tremendous contributions to science and engineering, but you just never know who might. You know, if I thought about Hedy Lamarr, I would never have connected her with Bluetooth or with Wi-Fi. And again, I ask if Hedy had not done what she did, where might we be? So I created this title, a little bit of tongue-in-cheek, taking a stab at alchemy. How many of you know what alchemy is? How many of you, that was not a good, how many of you do not know what alchemy is? Okay, so there are 2 people. So this is just for the 3 or 4 of you. I hope that's, okay, 3 or 4, maybe 5 people. So alchemy is that it's a medieval science that's about trying to convert base metals, very inexpensive, run-of-the-mill base metals into precious metals. So you could imagine taking something like iron or molybdenum and convert it into what? Gold, platinum. Wouldn't that be wonderful? That's the basis of alchemy. We're not going to show you real examples of alchemy here, but what I will show you is how this particular class of materials, early transition metal nitrides, on the addition of, so we'll start out, this class of materials starts out with what we call early transition metals. And for those of you who are not science-oriented, you'll have to bear with me because I'm going to go into detail, partly because I know we have a pretty broad audience here. But these base metals, very inexpensive, they're available, they're not rare, and again, they're very inexpensive. Interestingly, if I add nitrogen or carbon to them, and I have to put it in exactly the right place, if I can add nitrogen and carbon to them, their properties look more like some of these more expensive metals. And you can see, if you don't know the periodic table, that's, well, you can read it. Right? That's gold, platinum, very expensive, strategic elements that we make a number of really interesting and important products out of. And I mentioned they have to be put in the right place. So the place is, and I was hoping this would animate, but the place is in these interstitial sites. And these are spaces in between the metal. So if you could imagine, if I stack balls together as tight as I possibly can, you'll find little spaces in there. That space is of a certain size. It will only fit certain size atoms. If I take molybdenum and put nitrogen in there, that now becomes a nitride. The properties of that material on the addition of a small atom, relatively low concentrations, it changes very dramatically the properties of the material. And so, what are the potential uses? Well, carbides and nitrides are already used for cutting tools because they're very hard. They're used because they're multivalent. They can be used in energy storage applications. And then I see them, I've been working with this class of materials for about 20 years, and I actually think they're beautiful as well. There are applications in the jewelry and art area. Not so much, but the largest volumes probably, or certainly is in cutting tools. So the area that I'm most interested in and perhaps is most exciting for those in engineering and science is potentially the use of this class of materials as catalysts. And so catalysts are materials that make reactions go faster. And you might not appreciate this, but many of the consumer products that we use require something to make that reaction go faster. It'll go, if it's allowed to just sit there, you've probably heard the classic example, if I just take hydrogen and oxygen and let them sit there over some extended period of time, they'll turn into water, so H2O. But if I add a catalyst, that reaction, depending on the type of catalyst, I can make that reaction go very fast. And then if I'm thinking about a consumer product, I can take ingredients and make them into products more quickly. And that's a way of saving time, in some cases energy and money. And so catalysis is tremendously important. But what's important with regard to this talk is that these carbides and nitrides display precious metal chemistries, platinum group metal chemistries. They can do that for electrochemical reactions. They also can convert things that we're not really happy having around, like carbon monoxide, carbon dioxide. They can be used to convert carbon monoxide and carbon dioxide into fuels, and then sulfur removal, which is incredibly important for petroleum processing. And so just to follow up on this theme that catalysts are incredibly important, Oh, so one other thing I wanted to mention is that if you look at the cost of platinum, and this was on Friday, it's about $26,500 a kilogram. If I could replace some fraction of that with molybdenum-based materials, I've reduced the cost by maybe a factor of 1,000. So in talking about catalysis, I think it was, I was talking to Ann about why catalysis is so important. Many of us recognize that our cars require gasoline or some kind of fuel, right? You know where that fuel came from? It came from crude. So can you imagine if you've seen crude before, can you imagine putting crude into your vehicle? Michael, I hope you didn't say yes. Okay, you can't, well, so crude oil, it's dirty, the molecules are not formed in the way that we'd like them to become part of gasoline, so we have to do a lot of interesting things, all kinds of catalytic operations. And this was not meant to show you the detail. It's just meant to illustrate that we can go from natural resources like crude oil or natural gas to all kinds of consumer products, primarily as a consequence of catalysis, reshaping molecules, taking certain elements out, adding certain elements. This allows us to convert these relatively inexpensive natural products, and in this case they're fossil fuels, but anything, biomass for example, could also be processed. The economic value here is tremendous as well. In the last year or so, about $10 billion worth of catalysts were sold or marketed, and they affected about $10 trillion worth of products. So it's like a 10 to the 3 or 1,000 times enhancement in or leveraging of the cost of that catalyst. Catalysis is also important in emerging areas well, I'll start with hydrogen production. We're thinking about hydrogen for fuel cell powered vehicles. We also need hydrogen to process some of the hydrocarbons that I showed you on the last slide. We would not be able to drive cars without catalysts. Every one has a catalytic converter. I'm not saying that they all work, but they certainly have a catalytic converter in them to try and take out some of these pollutants that are regulated by EPA. And then fuel cells. Fuel cells present an opportunity for us to convert a natural resource that's benign, relatively benign, into electrical energy, and we could use that to power automobiles or houses or buildings and the like. And so catalysis is not only impacting traditional technologies, but also emerging technologies. And just to mention the Center for Catalytic Science and Technology here at the University of Delaware, as well as the Catalysis Center for Energy Innovation. So the University of Delaware, in fact, if you were to ask people across the country what is University of Delaware known for, I think one of the first things they would say is catalysis. So I'm happy to be here from that perspective. So in terms of what I want to describe today, now that I've done the introductory, covered the introductory material, I thought I'd talk about carbides, nitrides, and hydrogen. Hydrogen is a tremendously important reactant that we use for all kinds of chemical reactions, so I'd like to share with you some of our understanding of how hydrogen reacts or interacts with some of these materials. The carbides and nitrides have given us an opportunity to design catalysts in new ways, so it might offer opportunities to design something that solves a new problem or an emerging problem. And so I'll describe a little bit of that. And then one of the other areas that we've worked on for quite some time is trying to rationally design and synthesize these materials. So trying to control particle sizes. If you could imagine a catalyst, these are nanostructured materials. I'd like to control the shape of the particle. I'd like to control the size of the particle if I can, and we'll show you some results there. Oh, this one's animated. So I spent a lot of time trying to get this animated so it would show it spinning. Anyway, so that's an illustration of what molybdenum nitride looks like. Again, you have nitrogen in these interstitial sites, and you also notice that there's some vacant sites. There are what we call octahedral vacancies or interstitial sites, as well as tetrahedral interstitial sites. Hydrogen is also a very small atom, and one might imagine that you can also dissolve significant amounts of hydrogen in this same structure. And in fact, I'll show you results that clearly demonstrate that. You can do it very easily electrochemically. It's a little more difficult doing it thermally, but it can be done. In fact, if you were to compare nitrides, carbides, and metals, which also dissolve varying amounts of hydrogen, it's much faster for the nitrides and carbides. It also, in many cases, can be slightly exothermic. And this is in contrast to most metals. So there's a difference between the nitrides and carbides and metals, but there's some similarities in that you can dissolve a certain amount of hydrogen in their structure. And that could be really important as you think about their use. So the other part of it is that that hydrogen that's now, if you could imagine this platform is a surface. I have different places on this surface that I can populate with hydrogen and other reactants. Inside that material, which is underneath, I can also put small elements like hydrogen, if I have enough hydrogen. I might even be able to put some carbon or some additional carbon and nitrogen in. But for the sake of this talk, hydrogen on the surface, a little bit of hydrogen in the bulk. What I'd like to understand is how those different hydrogens interact with different molecules so I can determine how active the material is. I can see, is that interesting? I have another talk if you want to hear that one about. I find this fascinating. I'm trying to figure out how to convince people that this is like a really cool thing to understand. How subsurface hydrogen, which is not touching the surface, versus surface hydrogen interacts with molecules that are in the kind of floating around. That's an important question, so just trust me. It's an important question. So important that many people have been focused on this, in particular for metals. So if you looked at nickel, just as an example, nickel, in this particular case, Sylvia Sayre, who's at MIT, she found a way to, well, it's not that hard. You can put hydrogen on nickel. And the way these experiments are carried out, you have, in this case, a single crystal or just a material. I bathe it in hydrogen. I sweep all of the hydrogen away. What my hope is that a little bit will be in the subsurface, like in the platform, and some will be left on the surface. Then I'll bring in another molecule and see how it reacts with that hydrogen. Sound good? So in cases where she was sure, and her group was sure that all they had was surface hydrogen, and then they brought in that second molecule, in this case acetylene. Doesn't matter what it, it does matter what it is, but for our purposes, whatever that molecule is, hydrogen plus acetylene, you can see there's no reaction. So surface hydrogen, plenty of it there, it filled the whole surface, not active. On the other hand, when she was able to populate subsurface sites as well as surface sites, you can see, and you don't have to worry about this, she dosed, and then it dosed with hydrogen, exposed it to acetylene, heats it up, and you can see that different products are coming out. The important thing is that now, instead of seeing that there's no reaction, no significant reaction, there is significant reaction. Only because of this subsurface hydrogen. Without that subsurface hydrogen, no reaction. So we wanted to see if that would be the case with some of the nitrides and carbides that we work with. So, I challenged Brian, who's illustrated here. I'll say this for every one of my students, one of my favorite students. Okay. Every one of them is one of my favorite students. So I kind of challenged Brian to think about ways that we could selectively sort of populate subsurface and surface sites with hydrogen. So he went in the lab, started looking at different thermal treatment strategies, and came up with one that allowed him to vary the amount of hydrogen that comes out in these two peaks. And again, you dose, and then you heat it up, and you look at what hydrogen's coming out. We did some calculations, and we were able to show that, and I'm oversimplifying things, Brian, if you're listening, I'm oversimplifying this, but there is a surface hydrogen that's protic. It's a nitrogen-hydrogen bond. That is one of the principal reasons we see peak A. And then there's this hydritic hydrogen that's a metal or a molybdenum hydrogen bond. All of this is from calculations, but it's consistent with some of the experimental results as well. That will give rise largely to peak B. So if you can remember, A is a surface site, B is a bulk or subsurface site. If you can remember that, we're good. So we wanted to look for a reaction that might be kind of challenging, and one of the reactions is both commercially interesting as well as scientifically interesting, is Croton-aldehyde hydrogenation. And in this reaction, there are three principal products. If I don't tear up the molecule, if I leave it mostly intact and just add hydrogen to it, I can get croto-alcohol, I can get butyraldehyde, and then butanol. Croto-alcohol is the more valuable product, but it's the least thermodynamically favorable, which means that if I sat croton-aldehyde and hydrogen in a vessel for a long time, same experiment that we did with hydrogen and oxygen, just left it there for a long, long time, I'd get mostly a mixture of butyraldehyde and butanol. I would not get any croto-alcohol, my most valuable product from this. So we were trying to figure out, is there a possibility we could kind of alter the chemistry or the electronics of the nitride to enhance the selectivity to croto-alcohol. So we did the experiments, but first we had to figure out how to selectively populate the sites, and this is just an illustration of three materials, all of which have about the same amount of hydrogen in them, but we have a different distribution. This one has more surface hydrogen, this one has more subsurface or bulk hydrogen. You could imagine having a collection of these materials, maybe 40 of them, and then just checking to see what the selectivity is to these products. Sound interesting? Please say yes. Okay, good. So that's what we did. We don't have the whole spectrum mapped out, but you can see that there's a very strong correlation between the amount of subsurface hydrogen that we have and our ability to produce this croto-alcohol. What it suggests is that if we only have subsurface hydrogen, we will produce almost 100% croto-alcohol, which is a tremendous accomplishment. These are stoichiometric, what we call stoichiometric reactions, so it's not truly catalytic. We can't flow our reactants through and get these kinds of products yet, but we're working on strategies that might allow us to get these kinds of selectivities from this class of materials. So the first thought was that that hydrogen that's in the bulk kind of jumped out and attacked the croton-aldehyde. You know, because the croton-aldehyde is floating around out here, the hydrogen in the bulk is in the subsurface, so it's not directly in contact. So, you know, our initial thought was somehow a tunnel, we call it tunneled out, reacted with the croton-aldehyde. But then Brian again went back, he said, well, I don't believe that, so he started to do some additional calculations in collaboration with some colleagues at North Texas. And what they discovered is that electronically, that subsurface hydrogen, normally croton-aldehyde kind of lays down on the surface, but when you put subsurface hydrogen in it, it kind of stands up and the oxygen is attached to the surface. So that makes it more amenable to hydrogenation right at that oxygen. So it really is not so much about that hydrogen coming out and attacking the croton-aldehyde directly. It influences the bonding that then allows for you to have a higher concentration of croto-alcohol. And so again, we're working on ways to demonstrate that in a catalytic process. Let me talk about design, and in particular, some interesting ways that we can use nitrides and carbides, primarily because I didn't mention this at the beginning, but you can produce these materials with very high surface areas. If you know anything about catalysis, a traditional catalyst will have a high surface area substrate, which is relatively inactive, and then we'll put very active materials that tend to be expensive on top. And so that's a typical catalyst design. With the carbides, we can use them as supports and then put metals on top. So the conventional wisdom with regard to catalyst design, the way I grew up thinking about catalysis, the way many of our students today are being taught how to think about catalytic or catalyst design, is that we try to find a single descriptor. You know, that would be some characteristic that defines how that process works for this set of reactants and these types of catalysts. So if I were looking at syngas to methane, we call that the methanation reaction. I can plot out a reaction coordinate, thermodynamic reaction coordinate. I could then try to figure out which one of these characteristic steps is most important, correlate that with some energies or maybe even reaction rates, and then try to find that parameter that best describes, or that descriptor that best describes the catalysis. So in this particular case, you can see that the CO dissociation energy, which is associated with this particular step, is a good metric or descriptor for the catalytic activity. So we can go in and start thinking about designing a material based on our understanding of how carbon monoxide dissociates on the surface. But you'll recognize that many of these reactions, they're multi-step. And so one argument against using just this approach is that we know there'll be another step that becomes important. Once I fix one, there might be another one. So the people in the homogeneous catalysis community have been using this cascade or tandem strategy for many years. What they basically look at is a sequence of reactions that has to occur in order to make the desired product. And if I can map that out, I can probably get to my product more efficiently. And there are biological systems that work that way. We can only do certain things as a consequence of having cascade or tandem catalytic systems. They certainly will allow for us to intensify processes so that we can do more in a smaller volume. We'll do it in a greener way, which is also very important. The design is a little bit different. Instead of now looking for a single parameter, we will find different catalysts to catalyze individual steps that are involved in the reaction. So for example, if I'm trying to go from something like carbon monoxide, a waste material, and in some cases a problematic waste material, to carbohydrates, which might be in fuels, I could either try to find one catalyst that gets me from here to here, or I look at a sequence of catalysts that go through different intermediates on our way to a final product. And so I'm going to show you an example of our use of, some examples of our use of this cascade strategy. I mean, we used it for aldehyde water shift, water gas shift. These are probably not that important to you, except that the oxidation of aldehydes to acids. Acids are used in a variety of our consumer products, so we need them, I won't say desperately, but they're in tremendous need. And so this might allow us to use, instead of oxygen or peroxides, we can use water as the oxidant. We've also looked at CO2 hydrogenation, again, CO2 being a problematic pollutant. If I can convert that into something like methanol, methanol could be used as a fuel. Methanol is also a building block for a variety of other products, and so we've worked on putting catalysts together, in this case taking this iridium complex along with a metal carbide, supported copper catalyst. Together, they allow you to produce a substantial amount of methanol, much more than the individual catalysts produce. So there's some synergy between the two that's important. And so that was work that was done by 3 other of my favorite students. So the reaction that I'm going to talk about today, this is newer work in our group, or at least the group that I had at Michigan that I hope to bring some part of this research to Delaware, is ammonia synthesis. I don't know that I understood or really appreciated how important ammonia is before just looking at some of the background, but there's a huge market for ammonia, as you probably would imagine. It is the key ingredient in our fertilizers. In fact, if you look, about 50% of our population is fed as a consequence of synthetic ammonia that we make through this reaction, nitrogen plus hydrogen making ammonia. So an incredibly important reaction. It's also ammonia is a key constituent in a number of other chemical compounds and synthetic products. Importantly, it was discovered or commercialized based on discoveries by Fritz Haber and Carl Bosch. Fritz Haber was responsible for identifying catalysts that could be used for this reaction. Interestingly, the catalyst that's used today is very similar to the catalyst that was developed almost 100 years ago now, or more than 100 years ago now. And then Carl Bosch showed how you could scale this up to commercial quantities, which is important for the production of consumer products. The reaction itself is done under fairly severe conditions, high temperatures, high pressures, a relatively inexpensive catalyst, but it's inexpensive only in that we trade off the expense for the catalyst for almost extremes with regard to the processing conditions. So what we really like to do is identify ways to make ammonia at lower temperatures. The other challenges associated with this process, because of these temperatures and pressures, is that they consume tremendous amounts of energy. About 1% to 2% of all the energy consumed globally is due to ammonia synthesis. It might not sound like a whole lot, but just think about 500 quads of energy. 1% to 2% of that is associated with making fertilizers to feed the population. It accounts for about 3% of all the natural gas globally that's consumed. And then it produces about 320 million tons of carbon dioxide annually. So these are major issues that we're trying to address through the development of new materials. And so, again, you challenge your students, and sometimes they can come up with very interesting things. We're talking about this cascade concept. Most of the catalysts that were developed for this reaction, the thought was that the most important thing was to break this nitrogen-nitrogen bond. Of course, that has to happen in order for you to get to ammonia, this desired final product. But there are other steps. I have to break a hydrogen-hydrogen bond. I also have to form nitrogen-hydrogen bonds, and I have to form 3 of them, in fact. And so I have to look at each one of those individual steps, think about catalysts that might be useful for each one of those. So we started to think, well, is there a way that we might be able to put different materials together in order to accomplish this overall reaction? We're again going to use, and I didn't mention the name of it, these are called temperature program reactions. Dose a material with one reactant, heat it up in the presence of another. And we look to see if any products come out, anything other than what was there at the very beginning. And so in this particular case, I dose with nitrogen, sweep out the gas so there's nitrogen on the surface, then I flow hydrogen over the surface, and I look for products. In this case, we get ammonia, and you can see we get ammonia at 270 degrees, and then at 625 degrees. Do you remember the temperatures that we use for iron-based catalysts? I showed you on the last slide. This is it. 500, 400 to 500 degrees. So it kind of makes sense that if we were to run this operation commercially, it'd probably be in this temperature range. What we really like to find is materials that allow you to activate and produce ammonia at lower temperatures. So we started thinking, well, let's try to put materials together that not only activate nitrogen bonds, but also activate hydrogen, and maybe even address the hydrogen-nitrogen bond formation, which is emerging as one of the more important steps. So we thought about it. Of course, we wanted to try our nitrides and carbides for this reaction. We tried just a plain nitride. Just in this case, this is a carbide, excuse me. Just molybdenum carbide. You can see the temperature. We haven't done much with regard to temperature, kind of intermediate, what you would see for this commercial light catalyst, iron on alumina. 450 is still not bad, but what's most important is that the same dosing strategy yielded a lot more ammonia. So instead of getting about 25 micromoles of ammonia, we got about 125 micromoles. So a substantial increase in the amount of ammonia produced, but still not much in the way of adjusting the temperature down. So we put iron on the surface, and I'll show you some results a little later. This is this should have been anticipated, but put iron on the surface of this molybdenum carbide, and what you will see in orange is a little bit of the chemistry associated with just the iron catalyst, a peak here and a peak here, and then evidence of the molybdenum carbide chemistry here. Interestingly, we cycled through a lot of different metals, and we found one that was pretty exciting, and that's cobalt. Cobalt is not known to do ammonia synthesis, and so we were really surprised to see anything come out of this particular catalyst. We thought it would probably look more just like molybdenum carbide, but as you can see, there's a substantial amount of ammonia produced at low temperatures, which again is really exciting if you're thinking about a process that you want to, where you want to reduce the amount of energy consumed, the amount of CO2 that's emitted, and maybe even reduce the amount of natural gas that's consumed. This might this kind of catalyst might be very interesting. Again, these are more stoichiometric reactions. To do it in a process, you'd have to flow both the nitrogen and hydrogen through, and so that's one of the things that we will work on. So let me wrap up with just a few thoughts about how we synthesize materials, again, trying to control their structure and composition. So this is going to scare some people, but we take an oxide like ammonium paramolybdate. We'll take that oxide, it's fairly dense. We convert it into a carbide or a nitride, which has, and it's going to sound counterintuitive, but it has a higher density. If I maintain the same gross structure, but it has a higher density, you're going to get cracks. Those cracks reveal additional surface area. And so I can take a material that has essentially no surface area, about 1 square meter per gram, and convert it into something that has 120 square meters per gram. If I had about 10 to 15 grams of this material, and I could spread out that surface, it's about the size of a football field. So 10 grams of this material is equivalent to the size of a football field. The particles are very small. These are nanometer-sized particles, which is important. But perhaps more importantly, because this material is so reactive, I have to do something called passivate. I have to pass oxygen or some oxidant over the surface just to quiet it down so it doesn't just flame up. And so we do that passivation. Unfortunately, the passivation, if I do a surface chemistry experiment, you don't have to worry about what this means. Just the fact that the red, which is the passivated carbide, looks like the blue, which is an oxide. That is not what I want. What I really would like is to maintain the surface of the carbide, which looks different on this point of zero charge measurement. So we thought about it a little bit, and we actually came up with a way of avoiding air exposure, allowing the metal, if we were trying to absorb something or a reactant, to get to the surface without passivating the material, which is it sounds like a relatively simple thing, but it was kind of a big thing for our lab. And it ultimately allowed us to make a variety of really important materials. So as an example, without passivating the material, we then expose it to chloroplatinic acid, a common source of platinum for a platinum catalyst. And you can see the color changes, the amount of platinum in solution goes down. All of that platinum that was in solution is now on the surface. And if you did a formal oxidation state assessment, you would say that platinum is +4. It means in the simplest of terms, it's missing 4 electrons. I add it to the surface, and it gets back all 4 of those electrons. It got those 4 electrons from the material itself, so the material has been oxidized, but the surface that it sits on is now, the platinum that sits on that surface is 0 valent. So that's really important because usually I'd have to do some post-treatment to try and make it into 0 valent platinum. Structurally, it's a beautiful material, at least from my perspective. You produce these very thin layers of platinum. One of the challenges in catalysis is to control the structure of the metal that you put on the surface. In this particular case, you put 2 to 3 layers of platinum. And with the traditional catalyst, if I add more platinum, it'll grow up in this direction. If, again, this is representing a catalyst surface, it would grow up in this direction. What we've been able to discover is that for this particular support and some of these metals, it grows out in this way. And so if I can seed a site, I can grow particles 2 to 3 layers thick of metals that I'm interested in. Why would that be important? Well, with platinum, as expensive as it is, I don't want to have a lot of platinum in the bulk, like in the center of the particle. I want to have all of that platinum available. 2 to 3 layers is wonderful. I'll take 1 layer between the particle and the surface, 1 layer in between, and maybe 1 layer that's exposed to the reactant. So that was a tremendous finding for our group. It happens for a variety of other metals, in particular for copper and palladium, and so we've been able to make those catalysts. Doesn't work real well for iron, but we're working on strategies to make it work with these nickel, cobalt, and iron. But what we also found interesting, I mentioned that the material gets reduced. We add electrons to the platinum, and so it turns out that if you were to measure the reduction potential, which is an electrochemical property, and then compare that to the amount of that metal that absorbs on the surface, there's a pretty good correlation, which suggests that now we can start predicting, based on calculated or measured or whatever reduction potentials, we can start to predict which materials will end up with high loadings, reduced on the surface, and which ones will end up being sort of poor. So again, design strategies that might be useful if we were using these for commercial applications. So with that, and given the time, I think close to being on time, I hope I've been able to share with you some of the exciting results that we have regarding hydrogen and metal carbides and nitrides, in particular how subsurface hydrogen can impact the catalysis that happens primarily on the surface. I've talked about how we can use these carbides, high surface area materials, carbides and nitrides, as effective supports for cascade systems, executing some very difficult reactions at temperatures that prior to some of our work were not seen before. And then this thought that we might be able to not only control the amount of metal on the surface, but the structure of that metal and the size of the particles that are there. If we can do that, then we have the full circle. We can design, we can think about designing the material, we have strategies for synthesizing it, and then we know what to do with it. So with that, I'd like to thank you for your attention. I also want to take a moment to, again, thank Robin. I want to thank my wife. Tremendous amount of help from the College of Engineering staff and faculty. You know, it's going to sound like the Oscars, but I have to mention Anne and Joy and Julie and Lori, and I won't say most importantly, but I couldn't stop without mentioning Suzato, who was really helpful in setting all of this up. And thank you again for coming out, and if we have time, we'll try to answer some questions. Actually, I have a question. Were these open? Okay, good. I always check because you never know. Sorry.
So the short form of the question is, where do you see interdisciplinary opportunities? But let me expand a little bit. You've been here maybe for half a year, a little longer than half a year. You've seen, you know, different departments, mostly in the College of Engineering, but all over the campus. You've seen the strengths of these departments. Where do you see opportunities for combining some of these strengths, you know, putting them together with the goals of catalytic design, and maybe together formulate teams that could tackle some really grand challenges, and where we could become national leaders?
Yeah, you answered the question. So if you think about it, a lot of what we do starts with, in particular in engineering, it starts with some challenge. You know, many will characterize them as being grand challenges. Whatever it is, it's a challenge, an opportunity, a problem that we're looking at, trying to figure out what we can do to make it better. When we do say grand challenge, it heightens things a little bit. And typically, you're going to have more than one discipline contribute. It's not only, you know, if I think about our College of Engineering or any College of Engineering, you're going to have, for catalytic applications, you can immediately think of chemical engineers, material scientists, for the production of ammonia, an important ingredient in fertilizers. We might have people from our College of Ag, at the Ag College, abbreviated. We might have contributions from the business school looking at the economics. We might have environmental issues that we're looking at. Are we really able to make a dent in the CO2 emissions and the amount of energy that's consumed? So you can imagine for some of these things, something that might on maybe face value look pretty simple, ammonia synthesis, but there are tremendous opportunities for collaboration. And so one of the things that we're doing in the college, and I don't want to do too much publicity for the college, but one of the things that we're doing is trying to reframe what we do in terms of like intellectual challenges, or we call them, I mean, some have called them neighborhoods. We want to reframe the conversation around those. What are the major things that we can focus on collaboratively to make this a better place? And so, thank you for the question. I don't know if that was where you were headed with it, but as dean, I took the opportunity to. That's what deans do. You just. Other questions about nitrides or carbides?
Yes, Maciek Antoniewicz from Chemical Engineering. Is there any lessons you could learn from biology when you look at nitrogenases that can produce ammonia at 37 degrees Celsius? Any way to take any understanding from biology to design better catalysts? Absolutely.
So I would say, you know, our best example for the work that I've been involved with now is CO2 to carbohydrates. If you looked at photosynthesis as an example, biological process, there are multiple steps involved. There's energy transfer. There are all kinds of interesting electrocatalytic steps, catalytic steps. There are enzymes involved. And so if we could borrow that thought that you're going to need more than just one type of catalytic function, I think it will give us opportunities to address the challenges that we typically see for in sort of traditional catalysis in a different way. So absolutely, we see those examples. One of the challenges is, I mean, earlier in my career, I worked with someone, his name was Henry Wong. The thought was that we could take enzymatic materials and actually anchor them to the surface. So a commercial process, we'd like to have something anchored to a surface so it doesn't go along with the process stream. If we could anchor it, tried to look at ways to anchor those enzymes or biocatalytic materials, very, very difficult. So I think maybe we could do that. Maybe you can do that today, but we certainly can mimic. We can think about the steps that are involved, use them as examples, and build up our own non-biological catalytic systems as opposed to like a single system, a single catalytic material.
So Levi,
the hybridization of nitrogen?
No.
Okay.
The addition of cobalt, the addition of cobalt to your, it's not on? There we go. The addition of cobalt to your, I forget if it was nitride or carbide, molybdenum,
carbide.
That really dropped the temperature for ammonia formation remarkably. What's your working hypothesis for the role of that cobalt there? Is it hydrogen activation?
So if you remember, the carbide by itself does ammonia synthesis, high temperature. Some metals you put on the surface and they behave like they normally do. Cobalt is inactive. My suspicion is that right at the interface between cobalt and the molybdenum carbide, there's some kind of special site, and I don't have a description for it, but there's some kind of special site that helps finish the reaction. Moly carbide does nitrogen-nitrogen bond breaking. A lot of metals will do hydrogen activation. You can absorb hydrogen, atomic hydrogen. So what's left? What's the last reaction that has to be executed? I'm asking. No, so I break the nitrogen.
Nitrogen-hydrogen bond.
Nitrogen-hydrogen. So an argument, subject to investigation, is that at that interface between the two, we've created some sites where we can get, and I don't know if it's atomic nitrogen or maybe somehow there's something at that interface, because it's not cobalt. It's not the carbide by itself. Right at that interface.
What is the cobalt loading in those systems?
Maybe 5 to 10%. So there's enough of it there, and it's spread out enough that there's a significant, I mean, it's maybe 5% surface coverage, so there's enough. But I think that interface is where something kind of interesting is happening. And what we're left with, if we already can do nitrogen activation, nitrogen-nitrogen, we can do, I mean, hydrogen absorbs on a lot of metals. it probably is the formation of that nitrogen-hydrogen bond. That's what we're thinking. That's a working hypothesis.
Great. I didn't understand a lot of it, but I liked it. Very academic. Can you tell us a little bit about the story of how you moved into startups and your entrepreneurship part?
I could. So, I mean, I take the word engineer very seriously. You know, I like the basic science work that we do, but I also like seeing product come out of it. And so early in my career, I thought about, well, what could we do to really have impact? And so we were looking at a variety of different things, came up with one thing, and it's a long story, but Maria, my wife, is also kind of in the entrepreneurial space, and Robin got it perfect. I never considered myself, and I still don't consider myself an entrepreneur. I see myself as an innovator, an inventor. I'll come up with all kinds of, you know, some interesting things, but a lot of not so interesting things. But then if you have somebody who understands the value of what you have, they can turn that concept into something big. So you just have to come up with enough of those, find some people that you can work with. And fortunately, you know, she was right there across the dinner table. And so conversations about, yeah, literally, right across the dinner table. I was trying to think. Conversations about, well, you know, this could be kind of interesting. That could be kind of interesting. You know, and most of the time, I mean, it's like half of this audience probably, you know, this is probably not going to mean that much to you, but then there's something, yeah, that could be kind of interesting. Do that enough times, we found something, ultimately started a company grew, sold it, and what Robin didn't say, it was a big deal for us. You know, it was a big deal for our community, for not only the University of Michigan, but Ann Arbor and Southeast Michigan, so we got a lot of important publicity out of that. But it really was the consequence of me wanting to do something that's not just basic. You know, it really is something that could have an impact on society. That's what engineering is, solving problems that are of commercial and societal importance.
Trent Simonetti, undergrad chemical engineer. First of all, I just wanted to thank you for a really interesting, informative lecture. And I think earlier you had a slide, it was like cited molybdenum as $20 a kilogram, and then platinum as your $2,800 a kilogram. I just wanted to get like a ballpark estimation of the addition of the nitrogenous and hydrogen components to your carbides, how much that brings the price point of the molybdenum up.
There are less, so carbon, so we have, there are websites that you can go to. It'll tell you how much a carbon atom costs for cost analysis. Carbon and nitrogen, very inexpensive, so it adds very little. The processing will add some to the overall cost, but there's no way you're going to close that gap, a 3-order of magnitude gap in the cost. Now, the performance might not be as good as platinum, but if, you know, there's an argument. If we can spend 10 times more to get to something that looks similar, is that enough? We have an opportunity to make it 100 times less expensive than it might be if we continue to use platinum. And so there are materials like tungsten carbides that have reasonably high activities for fuel cells, just as an example. They're, let's call it 100 times less expensive. I can use 100 times more of that, or I can reduce the total amount so that the fuel cell, or at least the catalyst in that fuel cell price, comes down substantially. So all kinds of interesting ways to think about how the availability of a relatively low-cost material could impact the cost of the product in the end.
Thank you for your lecture, really appreciate that. I noticed that you gave scientific and visual attribution to many of your students in the work that they did. Could you talk just a little bit about ways in which you've taken student talent and other talent and integrated into your team research perspective as a research leader? And how you've encouraged some of the innovation that we saw today?
So this is going to be an unsatisfying response to that. I think part of it's just the culture in the group. You know, I spent a lot of time earlier in my career trying to, put the building blocks together for what I would consider a very effective, engaging group. And so from the beginning, I always thought about that. But then over time, you're adding, I had a group of 15, 17 students. You add one, they're going to get immersed in this culture that's already there. And the culture that I hope they would tell you this. It's a culture where we celebrate advances, but we also recognize that there are going to be tremendous failures. We're going to try. I'm not necessarily, I hope they would tell you this as well. I'm not out there trying to make a better material. My first thought is that if I can understand things that control how that material performs, then maybe I or somebody else or they could then figure out how to make it better. But if we focus on just trying to understand how materials work, what is the most important thing? How important is hydrogen in this mix, subsurface hydrogen in particular? How can we control the structure? I may not even have an application yet. I know that it would be important to control the structure, but how do we control that structure? If you start encouraging them to think that way, I think good things come out of it. And every one of them fortunately has a job. None of them have come back to the nest, so to speak. So I think they are reasonably happy with what we were doing. So it's just a culture that evolved over time, and they contributed to it. I was as a junior faculty member, I wasn't that much older than they were. In fact, my first two students were older than I was, so they had an important impact on how the group grew and evolved. So, thank you for the question, and thank you all for your.
I'm gonna answer that a little bit myself at the risk of revealing something I probably shouldn't. But at the point we were hiring Levi, Dennis Asanas asked me to make several calls to people who had worked with you. And on one of the calls I made, I said, tell me about Levi and what do you think about him? And the answer was this. Let me put it this way. When I left Michigan, I left my students with Levi because I knew he would take care of them.
I also had money, so.
All right.
No, he did. That was Phil, I'm sure.
All right. So we're going to stop the questions in this formal setting, but there's a reception right outside the doors here in the lobby of Mitchell. So hang around for a while, and you can talk to Levi, but also each other. And thank you, everyone, for coming, and let's give Levi another big thank you for this. Thank you.